So I'm gonna make a little video about everything we learned in lecture today. So right now we're kind of looking through enolate reactions, adding a nucleophile to a carbonyl containing compound and making an enolate. So to kind of draw it out, first we have our carbonyl. To a carbonyl, we'll add in a nucleophile. This nucleophile, what it will do is this nucleophile will come and react with this carbon here, which is relatively electrophilic because of this very electronegative oxygen on top. So it pulls charge electron density toward it, giving this partial positive charge and this one a partial negative charge. And we get this compound. And we have a negative charge here, since these electrons will go here. Okay, and so the thing about and so this is reacting a nucleophile with a carbonyl compound, but the problem with this is in neutral conditions, and it's too slow, not as fast as we want it. And so we introduce acidic conditions. You can also do this in basic conditions. So we'll start with our acetate, a simple ketone, and we will put it in acidic conditions. And so what happens when you have a ketone in acidic conditions? So a ketone itself okay, let's first actually talk about neutral conditions. So first we're going to talk about the equilibrium of a simple ketone acetone. Okay, so we have our ketone. And what usually happens is if you have this in solution, it will equilibrate, meaning go that side, that's moving, in these two concentrations. This form and also its enol form or enolate. Okay, and so this is called an enolate. And this is called a ketone. And the 8 at the end of these words signifies a negative charge. And so basically, when you have this, at equilibrium, you have a greater concentration of ketone. Equilibrium, you have a greater concentration of your ketone. However, we want to form an enolate because with an enolate over here, we can, actually forgot what was the purpose of an enolate. Oh yeah, we want to do electrophilic reactions with an enolate. So an electrophile inverts the positive charge. And so we want to have it, we're trying to get an enolate and do electrophilic reactions. So actually title this electrophilic reactions with enolates. Okay, I think I butchered that. Okay. Enolates. Okay. And so we have ketone at a greater condition when we do this in neutral conditions. Now, okay, this was just some random stuff over here. Now, if you do this in acidic conditions, so you introduce H+, you will still have your equilibrium favor a greater concentration of your ketone. However, however, we will have more enolate than the prior neutral conditions. And so to drive your reaction, what we will do is you will have an enolate here, and we have more of it. But remember, overall, our reaction still favors our ketone form. Okay? And I drew this so wrong. Here, 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 here. Okay. And this is acidic conditions. You can also do this in basic conditions. But the thing about if you do with basic conditions, okay, let's actually first do a reaction here. So I'm gonna add some bromine. So we're gonna start with our ketone, acetone. And so if you have this in this case, pretend this is the correct arrow. So if you have this in acidic conditions, you can get the enolate form. Remember enolate and enolate stands for negative things. And if you add in a Br over here, which will serve as our electrophile, so this will be our electrophilic carbon. I mean Br, more negatively charged Br. You do a reaction with this, you can get this electron density here to go and snap to that Br, and you can essentially brominate your ketone. So you'll end off with this. And you'll have like a Br hanging around negative charge. And your O here is back to neutral. Okay. Okay. So the key here is through acidic conditions, we'll get enough in our enol form. Oh, I made a mistake here. Okay. If you do this in, okay, actually, when you introduce an H plus, this H plus will actually go react and add over here. And so what happened is temporarily add here, and then it makes this carbon is still more electrophilic. Yeah, more electrophilic. And yeah, adds. And so okay. And now if you do this in acidic conditions, you will quantitatively get this product. Quantitative product. Now the problem comes in with basic conditions. Basic conditions is that first of all, so you will have our ketone, and I believe in basic conditions we will form our. I actually need to Google this up. 1 second. Let's see. Basic conditions react ketone to enol. Okay, so I think what happens when you react this in basic conditions, so you have your OH minus, this will come and obstruct. I made this so huge. You have your OH minus, will come and abstract a hydrogen that's like hanging out from here. So remember we have hydrogens here. And then we will form an enolate. Oh no, my bad. Over here and here. You have a hydrogen abstracted that can go there. And then, no, actually. No, yeah. So you'll get some initial negative electron density. And then this can essentially kind of go here. This will travel up here. So you'll get this. And this. So these are two resonance forms of our enolate. Um, Actually, okay, so the problem with basic conditions is that okay, over here we stop with this product, but in basic conditions, our product is more reactive, I think. I'm kind of confused. It's more reactive. I think what he was trying to say is our BR will brominate multiple sites. Brominate multiple sites. I don't know, but this is a question I guess I'll ask my professor. What a big question mark, so we can come back to this. Yeah, let's kind of get back to me. Yeah, my blue ink. So this is kind of us forming an enolate. 8 stands for negative charge. Over here, since we have H, it's an enol. But yeah. And also note over here, in place of Br, you can also do this with like other halogens. So II, Br, Cl, that. Still near ketone. Okay. We also discussed haloform reactions at one point in previous lecture. I've honestly forgotten what these are. Yeah, let's see. Oh yeah, and something to kind of note about this, this reaction. Okay, so reaction with enol is all in situ. And so what in situ means is it's all happening in one step. Like one step, we're gonna add our H plus N Br2. So it basically means like meanwhile. Yeah. Um, and I'm gonna quickly look up what a haloform reaction is because I generally forgot. Okay, so you have your ketone, you have your alpha carbon, you have your basic conditions, you have your halogen. Um, you first, oh, I actually don't know what's going on here. Okay, so basically, by definition, the haloform reaction is the reaction of a metal ketone with chlorine, bromine, or iodine in the presence of a hydroxide ion to give a carboxylate ion and a haloform. There is one aldehyde that undergoes the haloform reaction, which is acetaldehyde. So pH, this. Okay, so I guess I will kind of go through our mechanism. So to first initially copy and paste the definition of what it is. Um, let's see how it works. Metal ketone. Metal ketone. Okay, let me screenshot this step by step. Hey, bingo, glad to join perfectly. Okay. Let's kind of draw it on the side while we do it. So a haliform reaction is when you react a metal ketone. So a metal ketone, we have our carbonyl attached to a phenyl group. And then we have our methyl on this side. And so you react it with a halogen. So I'll write X2 in the presence of hydroxide ions. So their hydroxide ions are here. They use sodium hydroxide, and this is their halogen to give a carboxylate ion. Okay, so this is our haloform, I'm guessing, and I'm guessing this is our carboxylate ion, question mark. Let me actually Google what a carboxylate ion is. Okay, so carboxylate ion is basically just the conjugate acid of okay, just conjugate acid of a carboxylic acid, COH acid, okay? And so if you just add an H here, you'll have your carboxylic acid. You remove that H, that conjugate acid here is our carboxylate ion. And I think a haloform is just a fancy word for what is it haloform? Okay, so the molecular formula of a haloform is CHX3, where X is a halogen, can be replaced by, okay, so a haloform is essentially CHX3, so you have three halogens with one hydrogen. And yeah, and apparently I think the professor mentioned this in lecture, it makes good leaving group. So if you're trying to form a carboxylic ion, I guess a haloform reaction would be your way to go because haloforms, which are three halogens to a carbon, make a good leaving group. And then, so you have your methyl ketone over here. You're reacting it with our halogen. You're providing hydroxides. And so the first mechanism is we have our, let's make it a bit thinner, yes, I don't know. Okay, yeah. So our methyl, one of this, our hydroxide is deprotonating. And so we have H2O as a leaving group, not a leaving group, but a product, I would say. And then over here we have CH2 with a negative charge. It's huge. Negative charge. And we have our halogen over here. Let me check our haloform reactions in situ. Our haloform reactions in situ. Assume it is. I'm not sure. I would assume it is though. Okay. And then that deprotonates. We have our negative charge here, bromine. So this is like our positive end. I mean, negatively charged end bromine. Negative charge will come extrapolate that. And then we've got this. And so we have our halogen here. We have our C. We have our HHBr. We have this floating around. And this will react again with another hydroxide. Will deprotonate once again, another water molecule. Now we have our CHBr, we have Br, it will come again, take another bromine. And then we have another bromine ion sitting around here. This another deprotonation will happen. And essentially we'll get our third bromine made. And yeah. And the moment we have now 3 halogens, it will stop deprotonation, like the hydroxide won't deprotonate anymore. Instead, this hydroxide will react like a nucleophile, come attract at the electrophilic carbon here, and then push in those electrons, and we form this structure. We have our CBr3, which we said is a good leaving group. 3 halogens, kind of key here, I guess. And so we have our carboxyl. Is this a carboxylate ion? No, because there's no carbonyl group. And then we reform our carbonyl. And our OH is hanging about there. Now OH is here, carbonyl is here. H kind of deprotonate. Again, we have our carboxylate ion. And I'm guessing this reaction kind of cycle, carboxylate ion cycles, question mark. Actually, I'm not sure if it cycles. Did we start with that? Oh no, we didn't start with that. We started with the methyl group, so no, actually it doesn't. But yeah, this is our product, our carboxylate ion, which remember we said is the conjugate acid of a carboxylic acid in our haloform. To remember we said essentially CH, 1 hydrogen, and 3 halogens bonded. That's kind of the summary of a reaction. Okay. Now the next thing we covered in lecture was you can't do stepwise. Let's see. Okay. So we used hydroxides for the basic conditions, and we had an haloform reaction. Okay, actually kind of stepping back from haloform reactions and kind of returning back to our enol we formed earlier. So ketone, take acidic conditions, then we form OH, and we have our I'd say our, so this is enol over here. This is one way to do electrophilic addition reactions. Addition, or is it? I think it was nucleophilic because we already covered electrophilic. It's one way to do no. I think I'm tripping here. It's one how to do electrophilic addition. We did electrophilic aromatic substitution reaction. This is electrophilic addition to a carbonyl compound. Okay. So we have this react in acidic conditions and it equilibrates to our enol form. We can proceed with this where this will then act like our nucleophile and react with electrophiles and go on, blah, blah, blah. Now the second way is to form what we call an enolate. So we'll start again with ketones. Okay, in one case, we'll start a ketone and then we'll introduce a base. And what this base will do, will come and abstract a hydrogen. Draw the hydrogens out. Yeah. After abstracting a hydrogen, we will get here negative charge in the carbon, which will resonate to here. Here, oh my, where am I introducing this? Okay. And then we'll have a negative charge here. Yeah. And then, yes, this is essentially our enolate. Enolate is essentially an enol with a negative charge. 8 stands for things with negative charge. And then we can proceed and do this will then serve as our nucleophile. We can proceed and do an electrophilic reaction. And so the thing about electrophilic reactions with carbonyl compounds, so there's 2 ways to proceed. One way is to form an enol, second way is to form enolate. One thing to mention is that when you form an enol, these happen in situ. So like one step, everything you put everything in together. Think of like meanwhile. While for this one is specifically a two-step reaction, and you have to do it two steps. Because first, number one, a base deprotonates alpha carbon. So alpha carbon is essentially the carbon adjacent to our carbonyl compound. And that's really important for when we're forming an enolate because if our carbon here doesn't have at least one hydrogen, nothing can get deprotonated and we can't form our enolate. And yeah, so that's the first step. Second step is then doing the electrophilic reaction with our now nucleophilic enolate. Okay, and so yeah. Okay. And so another thing about this one is kind of limited. It can do few range of electrophilic compounds. And then for this one, we can do a wider range of electrophilic compounds. We can react with and kind of proceed and see, show you like this part. After you form your enol, so we're going to take electrophile example bromine, kind of goes through mechanism wise. Yeah, double charge. This nucleophile here will come take our electrophile, and then we will form a bond with that. And so what will happen is that will go there, oxygen will come here. Yeah, and we'll deprotonate. Okay. We'll take that oxygen will come back here. I have big wings too. And then we'll deprotonate itself, drop out H plus, and we'll get O. We'll get O. And then we've also had like BR attached. And that's kind of how you add electrophile to nucleophile. Okay. And then kind of going through the nucleophilic reaction over here. You have your, okay, so this was our enol over here. Here we're gonna have an enolate. Okay, we're gonna have an enolate here. Okay, and the thing about the enolate, which is kind of important, is our enolate has two resonance forms. So we can have our negative charge be on our oxygen, or we can have our negative charge be on our carbon. And there's two important things to kind of think about, and the pathway taken. So we can have our electrophilic either add here, and what will essentially happen is this nucleophile. How should I do this? Okay, let's erase these arrows. This nucleophile will come, abstract that, and then we'll form this. Whereas if we have our negative charge on our carbon, electrophile will be here. Oxygen, actually forgot. Yeah, I actually forgot how to do this. I think I'm doing this wrong. Actually, this alkene will stay there is what my notes is showing. I think that is very much so wrong though. Give me a second. Let me pull up my lecture slides. you guys, I figured out where I was going wrong. So what I was trying to do before is I was trying to take the electrons from our alkene bond and reacting with our alkene. And the reason I was doing that was because I was following kind of what I kind of did with the enol when I was reacting with the electrophile. But since we have a charge on both of these compounds, we want to use that electron density first to react with their electrophile. And so this will kind of snatch that. We'll form an electrophile attached to our oxygen. Voila. And then over here, this will snatch that, and we'll have our electrophile attached to our ketone right there. So two different compounds. And now the question is, do we take pathway A or pathway B? So the pathway is determined by the type. Pathway is determined by type of electrophile. And also kind of like reacting with what? Like when we say O, I mean like O or C negative. Okay. And then this is where kind of the idea of hard, soft stuff was introduced. So let's put it right. So we can start kind of treat this here. So let's take, for example, for our electrophile, we're going to use an alkyl bromide. Okay, so an alkyl bromide, for example, would be like, let's see, actually, pull this. Take CH3Br. So I believe this looks like your carbon is there. It's attached to a Br. Here, let's put our, okay. C, so you have H, and attached to a Br. Remember, our Br is more electronegative than a carbon. So electron density is pulled their overall dipole. So this is more negative, this is more positive. And so our electrophile is our carbon specifically here. And so we're gonna take this, we're gonna take this, oh, this is enolate, remember, not enol. And yeah, so if we react an alkyl halide, by the way, is like the general alkyl halide. So I'll use, for this to indicate, I'll use CH3X, so the X indicates halide. I'll do, let's see, CH3X, CH3X, and a reminder, this is our electrophile. This is our electrophile, and the carbon here specifically is what's going to be reacting. So its electron density will pull the carbon, and it will pull the carbon and push out the halogen. So what's happening here is our nucleophile is coming, taking this carbon, and it's giving the electron density to the halogen, and that kind of stabilizes the halogen because the halogen is now happy, it has an octet. So just hang around as I'll hang around as a leaving group. And then it will form OCH3 with this. This, okay? Or, okay, so that's if we were to go the oxygen pathway. Other way is if we went this pathway, so carbon would come take the carbon out here, and then OCH3 here. Okay, and by the way, I'm just demonstrating what two pathways is. I'm not saying this is what happens, but I'm demonstrating what would happen if we took a alkyl halide and reacted with our enolate with one of the resonance forms. Remember, like the actual structure is like a hybrid. We're kind of trying to see which pathway will favor. So this comes steal that here. Still got our carbonyl. We've now attached our CH methyl right there. And we've got like our halogen floating around, happy, overall negative, octet though. So yeah. Now the question is, which of these two pathways is favored? So let's write CH3 here so we understand, right? Does our electrophile react with the negative on the oxygen or the negative charge on the carbon? So my professor kind of brought back this foundational concept of like with like with like. And so what happened basically is our electrophile will react with what's like it. With what's like it. Okay. And our electrophile here is a carbon, and a carbon here is more similar to a carbon here. So this is our like with like. And so our electrophilic carbon actually prefer this pathway. Whereas this is not actually, well, I'm not sure actually if this actually happens at all, but this is the quantitative pathway, as in like we will have a high yield. We'll have this formed in high yield. Okay, let's see. Okay, and he kind of introduced this as like soft. Wait. So like, I think it was because having a negative on an oxygen is more soft than having a negative on a carbon. This is like hard. And so we will react with a hard pathway versus a soft pathway or something like that. I actually am kind of weak on this. I want to know why again. Preferred, but yeah, that's the preferred pathway. I don't know what he meant by hard soft, but he mentioned this statement in lecture. If an electrophile is more hard, again, this is my question. What does it mean to be more hard? It will go to, it will go to, it will go to that is more soft. Is more soft. Okay. So we've established having a negative is more soft on an O, whereas having a negative on a carbon is more hard. I think it's just because of like an oxygen can handle electron density better. But an electrophile, if it's more hard, it will go to something. If electrophile is more, it will go to carbon. Okay, wait, I'm mixed this up. This is actually, if it's more hard, it will go that is more hard. So this is our like to like concept, like with like. If electrophile is more soft, it will go to soft. Okay, so this is again like to like. Like with like. Harder to have when you can have, okay. And he also mentioned something like it's harder to have negative. I think kind of get it. So negative is like your negative density can either be on your carbon and oxygen, but it's harder for it to be on carbon because that's when you have an oxygen that's more electronegative. That's like the more stable pathway. And so our carbon is more hard because when you have an alternative of an O negative, it's harder to get carbon negative, you know? And our O is more soft because it's easier to get our negative on O than C. Okay? And so, yeah. So I guess I'm kind of stuck on our electrophile. How do we determine electrophile is more hard or more soft? So I'm gonna write here my question. How do we determine if electrophile is soft or hard? Well, I think it's not more about soft or hard. It's maybe what it's more similar to. Is over here our electrophile is a carbon, and a carbon is more similar to another carbon. And so maybe that's why I took that pathway. So that's kind of like my theory. It's making a lot of sense in lecture, but kind of got lost. Okay, finally done with our first page of notes. We have 1, 2, 3, 4.3 more pages to go. We got this. Okay. Next, he talked about a very important concept of choosing our bases. So, kind of refresher going back. You start off your ketone, you react that with the base. What the base does, it deprotonates this hydrogen, forming an enolate. So you have actually the negative starts there because that's where it's deprotonated. And then you get like resonance forms. So I'm just gonna draw both resonance form, resonance form, resonance forms. I don't know if I'm saying that right. You get these two. Okay. And then yeah. And then we react that electrophile. Remember, we have two pathways possible, so I'll just write electrophile here, electrophile there, because there's two pathways we can go. And so coming back to here, when choosing your base, you need to think how strong of a base do I really need? How strong of a base do I really need? And the reason we even mention this, and instead of mentioning, oh, we need a strong base or a weak base, is because it's not a uniform answer. Not, it's not yeah, it's not uniform, but depends on context. And I didn't catch this right, but I think the context is what's being extracted. What's being extracted slash deprotonated. Question mark. Yeah. Because that's like the base you're kind of competing with. And then also another reason, another consideration is that stronger bases are more dangerous and expensive. And so these are like health and economical considerations you want to take when you're choosing a base, right? Choosing a base, you want to make these considerations. Okay. So let's take then an alkane. Say we want to take a base, say we want to deprotonate the methyl here. So this methyl is attached to H's, and you want to make this a negative on a carbon. So when you're drawing this, your hand should literally shake out of, like, this is not correct. You cannot, wait, let's take a step back here, actually. Remember, having negatives on a carbon is very unstable. It's something, it's just very unstable. You don't have this. And so when you're going from, so when you're determining what type of base you need a really, really, really strong base to go from here to here because it's simply unstable. And if you look at the pKa, I'm actually really bad at the pKa stuff. The pKa of this reaction is apparently 50 to 60 range. For pKa, what you want to say, larger pKa means not a stronger base, means harder to deprotonate, or that base is, no, I shouldn't even say base, I would say for that the acid form is unstable. Well, what does that mean? Yeah, because here is our base, conjugate base. This is our acid. And the pKa of our acid is 50 to 60, which is really high, which means it's already quite stable in the acid form, and it's very hard to deprotonate because this base is very unstable, okay? And so the pKa for extracting hydrogen off a carbon is very high. It's above 50, and it's very unstable to do. So there's not really a base. We don't really have a good base. Don't really have a good base to reaction. Okay. Now the second thing, let's look at another acid-base reaction. Going back to ketones, here you have our carbonyl. We want to deprotonate this hydrogen. This is a symmetrical ketone, by the way. Symmetrical, and I'm saying symmetrical is because we deprotonate our hydrogen from this alpha carbon or this alpha carbon, they're both the same. Yeah. So if you add in our base, you can deprotonate it. You'll get our enolate form. Remember, this can resonate. Give us this. And the pKa for this is actually around the 20 range. And so what this means is that the conjugate base is more stable than for alkene we saw above here. Then for alkene, gonna change to the previous one. Yeah. Okay, so I need to head out soon, so I'm gonna actually take a break for this. Or should I finish this page? Okay, we have to run through this page. I think we can do this. Okay. Yeah. And okay, so if you look at it, how is it more stable? It's more stable because number one, you have resonance happening, so this negative charge can go here. That stabilizes the negative charge, and also because we have oxygen, which is a very electronegative, so you can think of it as inductive effects that better stabilizes our negative electron density. And so, yeah. Okay, now, let's look at another ketone. React it with a base. Actually, wait, not ketone, my bad. Let's say we looked at this, I don't know what it's called, but basically a carbon, alkene, react with the base, and we will actually form this, which can actually resonate to here. So kind of looking off this, what do you think the pKa of this will be? So to find the pKa, we know that pKa of this is a very high range, 50-60, because conjugate base here, the thing with the negative charge, is very unstable. Whereas this one is pKa is 20. We have resonance, which stabilizes the negative electron density. We also have an oxygen, which introduces inductive effects, very electronegative, also helps stabilizes the electron density. And so let's kind of look at the basis of, like, can you guess what the pKa is? So if you look, like, how are we stabilizing electron density? We're stabilizing with resonance. So it's pretty good. But we don't have an oxygen here. We're kind of limited at we don't have inductive effects. No inductive effects. So as you can predict, this will be lower than this, but higher than this. Higher because it's a bit more unstable because we don't have the oxygen. And so pKa for this is around 43. Yeah. Okay. And so now the question is, okay, so we have all three of them. Question is, what base can we use to, I would say, deprotonate over here? Okay. So we need something that can help us deprotonate this ketone. Now let's try looking at, what about a methyl? Let's take CH3. So this is a base. Is this base good enough? So you need to think about what the pKa is. Now we know the pKa of alcohols is around 16. And so, which means that the CH3O minus, this is our base. So you look at the conjugate acid of this is essentially CH3OH, which is an alcohol. So the pKa of this will be around 16. Okay. Um, so the question is, can we use this as a base? We actually cannot use this as a base because pKa of this is 16. And I think how it works is it's more stable for this to stay in its deprotonated form than for it to help out over here form this deprotonated form. So no, this won't work. So over here, I'll write we cannot use methoxide, which is CH3O minus, cannot use. Now let's look at another base. I forgot the name, but I think CH3NH minus. I think it's an amide. I don't know. Now, if you look at this, remember nitrogen-containing compounds have a pKa typically within the mid-35 range. And so if you try to react to this, it'll do a better job because it's more stable for this base to come and react with our ketone to form this base over here because it's more stable since it has pH 20. So this is pKa 35. So we need a base, I think it's greater than 20. I don't know if you can tell. Greater than. So I will say that CH3NH minus will work. And that's also something that's commonly used. Okay, that's kind of it. pKa. Okay. And yeah. So let's kind of do that reaction. We're going to take our ketone over here. We're going to take our CH3 and H minus our nitrogen. Remember this has a pK around mid-35 pKa, whereas this one has a pKa of oh wait, no, I made a mistake here. Oh yeah. this does have a pKa, like remember it's conjugate base, what it looks like, it's the enolate form, has a pKa of around 20. So we're gonna kind of react these two and kind of see what goes on. So the problem here is when you have this base over here. So what we wanted is we wanted the base to come and deprotonate this alpha carbon here, right? And so we're using this base. Now we come in with a problem.
What? Fix my car. Oh.
You're paying that out of pocket?
This base over here, instead of coming and deprotonating this alpha carbon, will actually come and react with our carbon of our carbonyl. So remember the carbon adjacent in our carbonyl is very like relatively positively charged. And so it will do a nucleophilic reaction instead of our wanted basic reaction. And so this will proceed then for our carboxylate. No, this is carboxylate. I forgot. Oh no, alkylic. This is called alkoxide.
Yeah.
And we have our thing attached